This is SpaceTime Series 25, Episode 89. Coming up on SpaceTime, the ongoing search for dark matter, another win for modified Newtonian dynamics over dark matter, and NASA's Mars Curiosity Rover marks 10 years on the surface of the red planet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have placed new limits on where the mysterious invisible substance known as dark matter could be hiding. Scientists with the Oscillating Resonant Group Axion or Organ experiment at the University of Western Australia have now ruled out one potential mass range where the hypothetical axion particle could exist. The axion is one of the leading candidates for dark matter. Dark matter makes up more than 80% of all the matter in the universe. The problem is, it appears to only interact gravitationally with normal or baryonic matter, the stuff stars, black holes, planets, moons, houses, trees, cars, dogs, cats and people are made out of. Scientists know dark matter is real because they can see its gravitational influence on things like galaxies, stopping them from spinning apart. It's the dark matter in these galaxies providing the additional gravity needed to hold them together. And subatomic particles, like axions and sterile neutrinos, are among the leading candidates for dark matter. Possible hints for sterile neutrinos are now starting to turn up in high-energy collisions in particle accelerators. As for axions, well, they were originally proposed as part of a solution for another major problem in particle physics called the strong charge parity problem in quantum chromodynamics. CP symmetry tells us that physics should be unchanged if particles were swapped with their antimatter counterparts, and if left-handed and right-handed particles were also interchanged. The problem is, we know the symmetry breaks down in the standard model through weak nuclear interactions, and it's also expected to be broken through strong nuclear interactions as well, of the sort which govern quantum chromodynamics, although these have yet to be observed. But the thing is, quantum chromodynamics effects produce an effective periodic potential in which the axion field moves. The oscillations of the axion field about the minimum of the effective potential, the so-called misalignment mechanism, generates a cosmological population of cold axions with an abundance depending on the mass of the axion. Now, with a mass above, say, 10 to the 11 times the electron mass, axions could account for dark matter, and thus be both the dark matter candidate scientists are looking for, as well as a solution to the strong charge parity problem. And that's where the Organ experiment comes in. Organ is searching for an axion candidate by looking for the photons that axions should convert into under strong magnetic fields. To do this, Organ uses what's called an axion haloscope. It generates the magnetic field using a big electromagnet called a superconducting solenoid. Haloscopes use hollow metal chambers to trap the photons produced by axions in the magnetic field, making them easier to detect. A dilution refrigerator cools the resonator to cryogenic temperatures of around minus 273 degrees Celsius, just above absolute zero, in order to remove the thermal noise which would mask axion photons. Axions of a given mass should convert to a photon at a specific frequency or color. But since we don't know the mass of an axion, Organ first needs to work its way through the different mass ranges, focusing initially on those where dark matter is considered more likely to exist. The study's lead author, Ben McAllister from the University of Western Australia, says if no dark matter signals found in one location, then either the experiment's not sensitive enough to hear the signal above the noise in the background, or there is no dark matter in the corresponding axion mass range. So the search would then move to the next mass range. And that's the process they're going through now. He says his team are now modifying the detectors to achieve greater sensitivity and enable wider searches probing a new range of potential axion masses that are as yet unexplored.
So the Organ experiment is a particle physics experiment based in Australia that is looking for something called dark matter. Dark matter, if you're not familiar, is one of the biggest mysteries in the universe today. To put it very simply, we know now that all the stuff that makes up people and planets and stars and black holes, all of the little bits of matter, the fundamental particles, all of that stuff makes up about 1/6 of all the matter in the universe. And the remaining 5/6 is this invisible, mysterious stuff called dark matter that we know is in the universe. We know it's all around us. It's actually passing through the Earth, passing through our bodies right now, and we just can't see or touch it, and we don't know what it's made of. So the organ experiment is one of a number of experiments around the world that are trying to get an answer to that huge, huge question. What is this enormous amount of invisible matter that makes up most of the matter in the universe?
How do you know it's there?
Yeah, it's a great question. If we can't see it, we can't touch it, how do we know that it's there? The short answer is, well, a couple of ways, mostly thanks to astronomy, various different astronomical observations, which is just a fancy way of saying looking at space with telescopes and looking at the way stuff moves around. And so what we find when we look at every scale of the universe, when we look at individual galaxies, when we look at galaxy clusters, when we look at the very, very large scale structure of the universe, we find time and again that we can't explain the way anything moves around in space if we only consider the stuff that we can see. So if you take like a galaxy, for example, like the Milky Way, our own home galaxy, it's this spinning disk. We can look at a galaxy like the Milky Way with a telescope, and we can say, okay, I can see blah, 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 1, 2, 3, 4, 5, 6, 100 million stars. And then you can say, okay, that's roughly how much mass all those stars should have, and this is roughly how it should be distributed. And then you say, okay, so looking at the stuff I can see, I can sort of say where all the mass is. And then knowing where all the mass is, you can say, okay, well then this is how much gravity there should be, because we know that mass is the thing that provides that gravitational force. So we can estimate how much gravity there should be in a galaxy and how it should all be pulling. And then from that, we can model how the galaxy should behave, how it should spin, how it should rotate. And what we find is that the galaxies don't move the way we expect at all. They spin much, much, much faster than should be possible if all of the gravity is coming from the stuff that we can see. And so far, the best way we can explain this observation is that there's a heap more invisible matter in the galaxies that provides extra mass, that provides extra gravity, and holds the galaxy together, allows it to spin around faster without breaking apart and parts being flung up into space. That's just one example. There are a couple of other examples on different scales of cosmology, but that's the general idea. We can't see it, but we can see it pulling on the stuff we can see.
And then the question becomes, well, what are the likely candidates for it? Back in the 1990s, there were two leading theories, WIMPs and machos.
Yep.
We've pretty well got rid of machos now as a possibility. There just aren't enough black holes in the universe. Even though we're finding more than we thought there were, there isn't enough black hole material out there to account for the 5/6 of matter needed. So what does that leave us with? That leaves us with weakly interactive massive particles, basically itsy bitsy stuff. Tell us about it.
Yeah, right. So just on machos, I mean, I'm not exactly a black hole guy, but as far as I understand, there is still a window in which primordial black holes, as they're called, small black holes, can be compelling dark matter candidates. But to talk more about this specific work, the two leading classes of dark matter candidates at the moment, as you mentioned, weakly interacting massive particles, which do what they say on the tin. They're particles that have mass and they interact weakly with the standard model particles. So they might have masses that are order of a giga electron volt, which in physics terms, for what it's worth, is about the same as a proton, about the same as a hydrogen atom. So that's kind of roughly how big these things would be. They might be, 10 or 100 times bigger than that, but that's the sort of rough order of magnitude. And those were a very popular candidate for a long time. They still are a candidate that people do experiments for. In Australia, there's a big WIMP detector being built in Stawell in Victoria. But over time, in recent years, an emergingly popular candidate for dark matter is this thing called an axion, which is a similar kind of thing to a WIMP, but it's much, much, much lighter. These particles, these axions, which are motivated from a different area of physics and have emerged as one of the most popular dark matter candidates, would be much, 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 much lighter than even a single electron, many thousands of times lighter if they were the dark matter. So there's a huge amount of dark matter. The axions make it up. That means there must be just like a preposterously large number of axions filling up the universe, which is quite an interesting thought, that we could be surrounded by a sea of tiny, tiny invisible particles that provide collectively enough mass to bind the galaxy together. This is currently one of the theories, and that's the theory that we're trying to test with the organ experiment. So axions are very well motivated dark matter candidates. People are very excited about them. And the nice thing about axions, as far as prospects for detection are concerned, is that axions are supposed to have this interaction with photons, which are particles of light. You can engineer the right conditions and force axions to convert into photons. If you like, you can take something invisible and turn it into a little flash of light, which is great because photons are a thing that we happen to be outstanding at detecting as a species, human beings are really, really good at detecting photons. So the ability to take this dark matter, this invisible thing that we can't see, and convert it into something that we're great at detecting opens up a lot of prospects for trying to understand the dark matter better if it is indeed made out of axions, which is what we're trying to do with Organ.
Now, normally when one wants to convert a subatomic particle into another subatomic particle, such as a photon, you'd run it through a xeon tank or something like that, deep under a mountain range. But that only works for neutrinos. This is very different. You're looking at a tank basically made out of magnetism.
Yeah, that's exactly right. So the axion interaction with photons is what's called a two-photon coupling, which means that you can have an axion, say it comes from dark matter, and you can interact it with a photon, and then they will annihilate, if you like, and create another photon. So that's a two-photon, one-axion interaction. That interaction can happen different ways. The two photons can also coalesce and create an axion. You can have an axion spontaneously decaying into two photons. There's different ways you can run that interaction. But the most common way that we use it, as far as detection is concerned, is the first one that I mentioned. We get essentially a big tank of photons, and we hope that there's dark matter passing through it, made of axions, and then some of those axions will interact with the photons that are inside the detector and convert into other photons that we then try and observe. The sort of experimental detail of that is, as you've said, that the photons that we use as the source photons, if you like, for the axions to interact with, come from a very, very strong magnetic field. So that's this is the devil in the details of the very small scale particle physics. Is it turns out that magnetic fields, like a fridge magnet or a magnet that you might use in a scrapyard to pick up a car, the magnetic fields are on a very, very small scale made up of photons. So we get a big, big, big strong magnet, and that's a big, big, big source of photons. Then the axions go through, they interact with that magnet, with those photons, and they convert into tiny little flashes of light that we can try and detect.
How do you get rid of the ambient warmth in the tank? You must cool it down.
Yeah, well, that's exactly right. So as you've said, things that are warm emit photons. If you've ever looked through a thermal imaging camera, then you have seen this for yourself. Anything that has any temperature is constantly emitting random little bursts of photon energy that would be way, way bigger if we just left our tank kicking around at room temperature. The random bursts of energy that it would emit in the form of photons would be much, much, much stronger than the very tiny, weak photon signals from axions that we're trying to detect. So we cool the thing down to very low temperatures using a fancy piece of equipment called a dilution refrigerator, which is just a really fancy fridge. It can cool things down to millikelvin temperatures. That's a few thousandths of a degree above absolute zero. It's colder than the vacuum of space. And we look for, we suppress the ambient thermal fluctuations enough that we can look for these tiny little flashes of light that come from dark matter. The axion doesn't interact with our experiment very much other than to convert it to this little flash of light. So as far as the axion's concerned, it doesn't see the fridge, it doesn't see the detectors at all, it just sees the magnetic field. So the axion's just doing its own thing. It's traveling along at a velocity that it has arrived at by thermalizing with the galaxy at large. It doesn't really see our detector until it converts into a photon. When the axion converts, it converts into a photon of a certain frequency, or color, if you like. We know that light is made up of photons, and on a very, very small scale, the different colors of light, including the ones we can't see, extending up into ultraviolet and down into infrared, all of those are just photons of a different frequency. They're little wiggles of electromagnetic radiation wiggling about at different rates. Our detector that is detecting these little flashes of light can only be sensitive to a certain band of photon frequencies at any given time, which means we can only detect these axion-induced photons if they happen to fall within that band. And this is one of the big challenges with doing these kinds of experiments, because the frequency of photon that will be generated when an axion converts into a photon is unknown. And that is because of conservation of energy. We don't know the mass of the axion, if the axion is the dark matter. Same goes for the width. It's one of the biggest challenges. That's why there's so many different candidates, is we know this dark matter is there, we know how much of it there is in total, but we don't know how big an individual dark matter particle is. They could be very, very, very light, or they could be very, very, very heavy. And the mass that it happens to have, if it is an axion, will directly correspond to the frequency of the photon that's generated. So we build our detector to search for a certain bandwidth of frequencies of photons, and that then means that we are sensitive to a certain range of axion masses. So when we do an experiment, we look in a certain range of masses, and if we don't see anything, as is the case with this study that we're talking about, we can't actually say, okay, that means there's no axions, that means axions aren't dark matter. What it does mean is we can say, well, axions aren't dark matter within this specific mass range, we've ruled out some region of what we call the dark matter parameter space. There's this huge, huge range of places that the dark matter could be hiding, and we're just sort of slowly scanning through it, ruling out different bits as we go.
One of the ideas about axions was that they were supposed to be particles that travel at the speed of light, which would mean they'd have no mass at all.
Yeah, well, the axions we're looking at are not light speed axions. They'd be virialized to the galaxy, which is just a way of saying they move around at a couple hundred kilometers a second. So very quick, but not quite the speed of light. But yeah, they'd be very light. There are lower limits on the masses that they can have if they are to form dark matter. Theoretically, you can imagine a universe that has axions in it, but those axions aren't the dark matter, and then all bets are off. They're just, axions are exotic particles. They can have any mass you like. But if the axions are going to be the dark matter that's responsible for the way galaxies move and stuff, then there are limits you can place. They can't be any lighter than this. They can't be any heavier than this, because then, for details I won't go into, you just can't make the galaxy models work. Yeah. So you can put some rough bands on it, but it's still huge. It's a really, really big range, which means that there are lots of different experiments around the world that are complementary.
When we talk about dark, we often think about dark energy as well. The other big dark from the 1990s that people are talking about, the issue there is that there's always the possibility that maybe we don't understand type 1a supernovae as well as we think we do, or we may not understand exactly where we are in the cosmic web of the universe as well as we think we do. And both of those parameters would change our understanding of what dark energy is likely to be. Is there any way we could be in a similar situation with dark matter where we simply don't really understand the existing 17 particles of particle physics to really know what we're looking at?
Yeah, it's a great question. And the short answer is, of course, yeah. I mean, our observations that lead to dark matter are gravitational observations. So the other thing you can say from those weird gravitational observations that we can't explain is, okay, maybe we just don't understand gravity as well as we think we do. And maybe there is no dark matter and we just need better models of gravity, and then we can clean up all of these existing problems. And that's a perfectly fine and valid theory to have, or hypothesis, I should say. And indeed, people do work on that. That's the alternative explanation for these things. As yet, within the particle physics, or within the physics community, that is, I mean, people still work on it and are looking at it, and it's very valid research to do. It's not the preferred or the what's considered the more likely outcome for a couple of reasons. One, no one has been able to write down a model of gravity that explains all of the stuff that can be explained by the introduction of dark matter. So that's a big problem. If somebody was to write one of those models down, then it would merit some very serious consideration, and people would be very interested in seeing it. The other thing is, if you ask me, I mean, why should it be surprising that there's new particles? I mean, it was only fairly recently that we discovered the Higgs boson, and only fairly recently before that we discovered a bunch of the other ones that we now consider the standard model. So, like, what are the odds that this exact time in human history just happens to be the time that we've figured out everything that there is? It would be a real point of hubris of us, in my opinion, to say that we know everything that there is in the universe. It shouldn't be surprising, in my view, that there's other stuff out there. So I guess it's definitely possible, and it's an avenue that people consider, and is one of active research. But at the moment, at least, the dark matter hypothesis is considered broadly more likely, and at any rate, it has to be done. You need to pursue both things. That's how it works. Again, it's part of this collaborative mindset. You've got to pursue all options. That's how science works. And if it turns out there's no dark matter, then it turns out there's no dark matter, and there's some other answer. But we had to look for it. I'm at a conference right now, meeting with the other experiments that do this kind of work in Germany, where we essentially say, all right, we're going to look here. And it's this big international collaborative effort where we say, all right, we've looked here, we didn't find any axions here. And other people say, okay, cool, we've looked here, we didn't find any axions here. And we're just divvying up this space and scanning through it and ruling out different possibilities and narrowing it down. And things are really accelerating at the moment. This community is still relatively young as far as particle physics is concerned, and it's really progressing at a really exciting rate. So it's a very exciting time for axions. We're starting to really scan through a large amount of the parameter space, and if the axion is out there hiding in the dark matter, we will find it.
That's Dr. Ben McAllister from the University of Western Australia. And this is SpaceTime. Still to come, what if dark matter isn't the answer? What if it's modified Newtonian dynamics? We'll explore that with some exciting new evidence in a moment. Also, NASA's Mars Curiosity Rover marks 10 years on the surface of the red planet. And later in the science report, new evidence triggers fresh calls for a truly independent investigation into the origins of COVID-19. All that and more still to come on SpaceTime. Astronomers have unexpectedly found strong evidence supporting modified Newtonian dynamics, or MOND, rather than dark matter, to best explain observations of the gravitational tidal effects in the Fornax Cluster on a population of dwarf galaxies. Now, if confirmed by further observations, the findings, reported in the Journal of the Monthly Notices of the Royal Astronomical Society, are expected to ricochet through the world of physics and astronomy. Dwarf galaxies are small, faint galaxies that can usually be found in galaxy clusters or near larger galaxies. They can be affected by the gravitational influence of their larger companions, causing what are known as gravitational tides, which pull differently on different parts of the dwarf galaxies. The thing is, some of those gravitational tide changes should be countered by the influence of the dwarf galaxy's dark matter halos. And that's where these studies of the Fornax Cluster come in. They show that some of these dwarf galaxies appear distorted, as if they had been perturbed gravitationally by the cluster environment. One of the study's authors, Pavel Krupa from the University of Bonn and Charles University in Prague, says these perturbations in the Fornax dwarfs aren't expected according to the standard model. That's because the standard model predicts that the dark matter halos of these dwarf galaxies should at least partly shield them from the tides raised by the cluster. The authors analysed the expected level of disturbance in the dwarf galaxies. That should depend on their internal properties and their distance from the gravitationally powerful cluster centre. Galaxies which are large in size but with low stellar masses, and galaxies close to the cluster centre, should be more easily disturbed or destroyed. They compared the results with their observed level of disturbance, evident from images taken by the European Southern Observatory's Very Large Telescope, the VLT, in Chile. The comparison showed that if one wants to explain the observations in the standard model, the Fornax dwarf should already be destroyed by the gravity of the cluster centre, even when the tides it raises on the dwarfs are 64 times weaker than the dwarf's own self-gravity. Not only is this counterintuitive, but it also contradicts earlier studies, which found that the external force needed to disturb a dwarf galaxy is about the same as the dwarf's self-gravity. The authors say the findings show that the observed morphologies of the Fornax dwarfs simply can't be explained by the standard model in any self-consistent way. So, they repeated the analysis, this time using Modified Newtonian dynamics, or MOND. Now, we've talked about MOND before on the show. It's a hypothesis that proposes a modification of Newton's law of universal gravitation to account for observed properties in galaxies. First published back in 1983 by Israeli physicist Mordechai Milgram, the hypothesis' original motivation was to explain why the velocities of stars in galaxies were observed to be larger than expected based on Newtonian mechanics. It's an alternative to the hypothesis of dark matter in terms of explaining why galaxies don't appear to always obey the currently understood laws of physics. Instead of assuming dark matter halos surrounding galaxies, the MOND hypothesis proposes a correction to Newtonian dynamics, by which gravity experiences a boost in the regime of low accelerations. The authors say they weren't sure if the dwarf galaxies would be able to survive the extreme environment of a galaxy cluster in MOND due to the absence of protective dark matter halos in this model. But the results show a remarkable level of agreement between the observations and the MOND expectations for the level of disturbance in the Fornax dwarfs. Of course, this isn't the first time that we've reported a study testing the effects of dark matter on the dynamics and evolution of galaxies, which has concluded that the observations are better explained when they're not surrounded by dark matter. That's not to say MOND can explain everything, but the number of publications showing incompatibilities between observations and the dark matter paradigm is increasing every year, and that's interesting. This is SpaceTime. Still to come. NASA's Mars Curiosity Rover celebrates 10 years on the surface of the red planet, and another Blue Origin flight reaching for the edge of space. All that and more still to come on SpaceTime. NASA's Mars Curiosity Rover has celebrated its first decade exploring the red planet. Despite a few signs of wear and tear, the Intrepid six-wheeled mobile laboratory is about to start an exciting new chapter in its mission as it continues to climb Gull Crater's central peak, Mount Sharp. Since its arrival 10 years ago, Curiosity has driven over 29 kilometres and climbed more than 625 metres above the crater floor as it continues its search for evidence that billions of years ago, Mars had the sorts of conditions needed to support life. The rover's already examined 41 rock and soil samples using a suite of scientific instruments, learning what they reveal about the red planet's geology and climatic history. Scientists now want to understand Mars's transition from a warm, wet world capable of hosting life into the freeze-dried desert it's become today. Curiosity achieved its prime directive early on in the mission, determining that liquid water, as well as the chemical building blocks and nutrients needed for supporting life, were all present in Gull Crater for tens of millions of years. The crater once held a lake through which a river flowed, and the size of the lake waxed and waned over time. Each layer higher up on Mount Sharp serves as a geological record of a more recent era in the Martian environment. Curiosity's also studied the red planet skies, analysing the atmosphere and capturing images of shining clouds and the two drifting Martian moons, Phobos and Deimos. The rover's radiation sensor is also busy, constantly measuring the amount of high-energy radiation the surface is exposed to. This will provide important data which will be needed to keep future astronauts visiting the red planet safe. Curiosity's mission was recently extended for another 3 years, allowing it to continue its exploration. Now, the Intrepid rover is driving through a canyon which marks the transition to a new region, one which is thought to have formed as water began drying out, leaving behind salty minerals called sulfates. And scientists are seeing strong evidence of what can only be described as dramatic changes in the ancient Martian climate. The question now is whether the habitable conditions that Curiosity found earlier on in its mission persisted through these changes, or whether they disappeared, never to return, or whether they came and went over millions of years. Mission managers plan to keep Curiosity exploring this sulfate-rich area for the next few years. Their primary targets include the Gettysvallis Channel, which may have formed during a flood late in Mount Sharp's history, and large cemented fractures that show the effects of groundwater higher up the mountain. In order to keep the science coming, NASA's Jet Propulsion Laboratory in Pasadena, California, has a team of hundreds of engineers and technicians keeping Curiosity rolling. They catalogue every crack in the wheels, they test every line of computer code, and they study every rock drill proposal to make sure that Curiosity can safely undertake its mission millions of kilometres from the nearest roadside service. For example, Curiosity's robotic drilling process has been reinvented several times since landing. At one point, the drill was offline for more than a year as engineers redesigned its use to be more like a handheld drill. More recently, a set of braking mechanisms, they allow the robotic arm to move or stay in place, suddenly stopped working. That required a workaround solution. And to minimise damage to the wheels, engineers are keeping a sharp eye out for treacherous spots like the knife-edge gatorback terrain they recently discovered, and they've also developed a new traction control algorithm to help. Curiosity's power comes from a long-lived nuclear battery rather than solar panels to keep operating. As the plutonium pellets in this battery decay, they generate heat, which is then converted to power. Because the pellets gradually decay, the rover can't do quite as much in a day now as what it did every day during its first year of operation. So mission managers are carefully budgeting how much energy the rover uses every day, and they've figured out which activities can be done in parallel, multitasking to optimise energy availability. And before any instructions are sent to Curiosity on Mars, they're first tested out on Maggie. That's Curiosity's rover double here on Earth. This report from NASA TV.
The Curiosity rover set out to answer a big question. Could Mars have supported ancient life? Now we know the answer, but there's still so much more to learn.
To help NASA's Curiosity rover safely explore the surface of Mars, engineers here on Earth use a nearly identical sibling named Maggie. This full-scale engineering model helps the team practice operations in the Mars yard at NASA's Jet Propulsion Laboratory. I'm Raquel Villanueva, here with Curiosity Deputy Project Scientist Abigail Freeman. Her team is celebrating their 10th year on the Red Planet. Where has the rover traveled to in the past decade?
Well, we've spent the last basically 10 years Martian mountain climbing. Curiosity landed at the base of a big mountain named Mount Sharp that is made of layers of rocks. So we're climbing the mountain to give us a snapshot of Martian history. We've driven about 17.5 miles, and more impressively, we've climbed over 2,000 feet in elevation up the mountain. We're all the way up in these hills now. It's pretty spectacular.
With all that climbing, how is Curiosity doing?
Pretty good, actually. You know, all of our science instruments are working just about as good as they did when we landed. We have nearly our full capabilities. The arm and the drill and the rover, they're a little bit arthritic, so we have to be a little bit gentle when we use them. And our wheels are a little bit beat up. The wheels on Maggie look great, but we have some test wheels that we've really destroyed.
And how do you decide where the rover is going to go? Do you work with other NASA missions?
You know, the data from the Mars orbiters have been really helpful. The spectrometers, that's the kind of instrument on Odyssey and Mars Reconnaissance Orbiter, have told us where the interesting minerals are and where the best places to go to look at changing environments are. And then in particular, the cameras on the Mars Reconnaissance Orbiter, they're so good and they're so helpful at allowing us to find the safest way that we can climb this mountain.
What would you say is the biggest discovery your team has made?
You know, Curiosity was sent to Mars in order to answer a really big question. Did Mars have all of the ingredients that we know life needed? And 10 years later, not only have we given that answer a definitive yes, but we've also seen that those ingredients were around for tens of millions of years.
And what's next for Curiosity?
We can see from orbit that we're getting to a place in the mountain that likely records a pretty dramatic change in the sorts of environments that we're around. You know, the lakes that once filled Gale started to dry out, and we're getting to that period in time. So we're really interested in answering how long did these habitable environments persist as Mars and Gale Crater went through these pretty big climate changes. I just can't wait to see what's next. We've seen hints that the rocks are going to be very different very soon, and so I'm really curious what we're going to find.
Well, that is an exciting new chapter for you, and congratulations on 10 years. Thanks, Abigail.
Thanks so much.
This is SpaceTime. Still to come, another Blue Origin flight reaches the edge of space. And Beijing's come in for more criticism following the deorbit of yet another out-of-control spacecraft. All that and more coming up on SpaceTime. Blue Origin's New Shepard has successfully undertaken its 6th space tourism flight to the edge of space. The 11-minute Joy Flight N22 carried 6 passengers from the West Texas launch pad up to and beyond the Kármán line, marking the official start of space at an altitude of 100 kilometers.
The access tower for the crew capsule has been pulled back. The aft fins going through the motions, these fins help direct the vehicle on ascent and descent. The BE-3 engine is gimbaling. This is the primary control authority for the vehicle on ascent and descent, and of course critical for that soft landing on the landing pad. With just 30 seconds to go for today's launch, it's time to hand it off to Mission Control and launch this rocket.
Sky engine journal, T-minus 10, 9, 8, 7, 6, 5, 4, command engine start, 2, 1.
Shepard has cleared the tower and is heading to space. Godspeed, Titanium Feather. We are gaining speed as New Shepard gains altitude. We started at about 3,700 feet above median sea level, and that's where Launch Site 1 is located. We've hit our next milestone, Max Q, the point where aerodynamic stress on the vehicle is at its maximum, and that BE3 engine gets to flex its muscles, throttling down to reduce those stresses. Our next milestone will be main engine cutoff, but in the meantime, the BE3 is back to 110,000 pounds of thrust, powering New Shepard and its crew to space. And it looks to have been a successful main engine cutoff, with the vehicle traveling at more than 2,000 miles per hour and 200,000 feet of altitude. Our next milestone will be separation of the crew capsule and the booster for zero-G. Capcom will momentarily cue the astronauts to unbuckle their harnesses after separation. Congratulations to all 6 crew of the Titanium Feather. They just officially became astronauts with an apogee well over 100 kilometers, the internationally recognized boundary line of space. Both the crew capsule and booster are now descending. The forward fins deployed as that rocket is now reaching its atmospheric pierce point, returning from space and entering the atmosphere. Those control surfaces that raise the center of pressure on the vehicle now have a little bit of air pressure to push against. That's the ring fin and the forward fin, and the booster will be reaching its maximum re-entry velocity here just under Mach 4. Starting to slow down here now, the wedge fins, the steering fins, and the ring fin all working together, earning their keep to guide this booster home. Great. There it is, engine ignition, engine relay coming in for a landing. Booster touchdown. Welcome back to Earth, New Shepard. For a lot of us at Blue, this moment in flight is one of our proudest moments, really showcasing what the BE3 engine and the New Shepard booster are capable of. Really just incredible engineering. No matter how many times we've seen this happen, it just never gets old. It's a live booster landing, nice and softly onto that landing pad. You can't help but want for this to happen. At the bottom of the BE3 engine, we're venting any excess propellants. This is a key step in the reusability of this booster. We'll be able to purge with inert fluids and keep this booster clean. The crew capsule coming back down again, its gumdrop shape, a little slower to re-enter Earth's atmosphere. We should have the drogues here shortly. There they are. Drogue chutes are out. I count 3. And those drogue chutes have now pulled out the main chutes that will begin to fill with atmosphere. And the crew capsule looks to be maybe a little south or southwest of the landing pad, and of course that great West Texas backdrop. So as we come in here softly for a landing, those landing systems will engage, measuring the height above the ground to fire that innovative retro thrust system that kicks up the dust but makes for a very soft landing. Touchdown, Titanium Feather. Welcome back to Earth. So now our team is preparing landing safety operations and recovery of our astronauts from the crew capsule.
New Shepard's last flight occurred on June the 4th. Beijing's come in for more criticism following the deorbit of yet another out-of-control spacecraft. Unlike the disused spacecraft of most other spacefaring nations, which are brought down in a controlled manner, China simply allows their space junk to fall back to the surface in an uncontrolled fashion, bouncing off the upper atmosphere and then re-entering wherever it may. The latest examples were Beijing's Tianzhou-3 cargo ship, which had brought supplies to the Tianhe core module of China's new space station, and an upper-stage Long March 5B booster, which carried the space station's new Wentian science module into orbit. Mission managers in Beijing had no idea where the booster would eventually fall back to Earth. Eventually, debris from the 25-ton booster hit the Earth's upper atmosphere over the western Indian Ocean, then crashing to the ground over a wide area near villages in Malaysia and Indonesia. The wreckage included large sections big enough to have caused death to anyone in the way, and it's still not known if any highly toxic rocket fuel propellants were included in the debris trail. China has allowed Long March 5B rocket stages to crash back to Earth in an uncontrolled manner at least twice before, once in the Ivory Coast back in May 2020. Then again in May last year, when large sections of another Long March 5B booster crashed down in the Indian Ocean near the heavily populated Maldives Islands, also after launching elements of the Tiangong space station. These followed the prototype Tiangong-1 space station, which crashed into the Pacific Ocean near Tahiti back in April 2018. That was another uncontrolled deorbit, made even worse because Beijing tried to cover up the fact they had no control over what was happening until it was finally exposed by the European Space Agency. Last year, NASA accused Beijing of failing to meet responsible standards regarding their space debris. In fact, many spacefaring nations have slammed China's space officials for letting Long March 5B cores become big chunks of space junk, which, as we've shown, has happened on all three of the rocket's missions to date. And let's not forget, China also drew heavy criticism after using a missile to destroy a disused weather satellite in 2007, creating the largest ever debris field in space. And that's still today posing problems for safe space navigation. China is already the world's largest greenhouse gas producer, pumping as much CO2 in the atmosphere in 1.5 days as what Australia does in an entire year. And they now have the title of producing more space junk than any other nation as well. China's growing concern about the success of America's X-37B space shuttle program has seen Beijing launch its own reusable experimental spacecraft. The flight aboard a Long March 2F rocket from the Zhuquan Satellite Launch Center in northwestern China's Gobi Desert will see the spacecraft test a number of new technologies in orbit before eventually returning to Earth. While little is known about the orbiter, we do know a fair bit about the Long March 2F rocket, which is normally used to launch China's Shenzhou manned spacecraft. It has a payload capacity of around 8 tons to low Earth orbit, so that places at least some parameters on the size of the new experimental spacecraft. Beijing's last reusable experimental spacecraft mission was back in September 2010. It remained in orbit for less than 2 days before returning to Earth. China claims that mission was a complete success and resulted in major breakthroughs for China's reusable spacecraft research program. Beijing claims that once its reusable spacecraft enters formal operations, it'll be able to offer round-trip services to orbit which will be more convenient and affordable than existing options. Russia's just launched a spy satellite designed to spy on other spy satellites. The Cosmos 2558 Inspector craft was launched aboard a Soyuz 21V rocket from the Plesetsk Cosmodrome 800 kilometers north of Moscow. And this is where it gets interesting. The spacecraft was placed on the same 435 kilometer high orbit and on the same orbital track as America's USA 326 spy satellite, which was launched from the Vandenberg Space Force Base in California back in February aboard a Falcon 9 rocket on NROL 87. The Russian satellite's orbit sees it pass to within 73 kilometers of the American spy satellite. The launch comes after USA 326 was recently noted to deploy what appears to have been a smaller satellite, which was then placed into a separate orbit. Neither Moscow nor Washington are saying what their respective satellites are up to. But we do know the latest Russian intercept follows a similar encounter back in 2020, when 2 Russian spy satellites maneuvered to within 160 kilometers of another American spy satellite, the USA 245. We live in interesting times. A new theoretical study suggests that oceans and water-rich worlds could be enriched with electrolytes, including salts such as sodium chloride, which is an important factor in the search for life. A report in the journal Nature Communications claims the authors wanted to know if minerals could make it into the liquid water surface on planets where the high pressures create an ice sheet between the mineral-rich rocky core and the watery surface. Using computer modelling simulations, they found that salts like sodium chloride could be transported through the ice sheet into the watery oceans above. An accompanying editorial suggests that this study offers the most convincing argument so far in resolving the dilemma of large planetary hydrosphere habitability. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.